Hello, welcome again to this presentation on Machine Foundation. This is Lecture 2, wherein I'll introduce you to the basic terms in vibration theory. So the question that would obviously come from your end is, why not straight away start with the Machine Foundation rather than starting with the vibration theory? So the answer to this question is clear from the term relevance of this content. So as I rightly pointed out to you in the earlier video, if you want to compute the dynamic characteristics of a machine foundation system, namely its frequencies as well as its dynamic response under a set of exciting loads, the knowledge of the theory of vibration is essential. So that's why we straight away start from the theory of vibration. I will take you to the various lectures in the theory of vibration in the subsequent videos before getting into the details of the machine foundation. So let me introduce you to the definition of some basic terms. The first one is the spring mass system. So if you want to study the dynamic response of any physical system, you require a mathematical model. And the basic requirement of this mathematical model is that it must be simple enough. Secondly, it must be able to predict with a sufficient accuracy the response of the actual physical system. And finally, it should not be computationally intensive. So to study the dynamic response of any physical system, the most simple mathematical model available is the spring mass system, which is shown over here. This spring mass system is basically the simplest model that is used to explain some of the basic concepts in the theory of vibration. As you can see that the system consists of a spring that represents the system stiffness, a damper that provides you the way of representing the system damping, and finally we have a lumped mass that is used to model the system mass. So here, as you can see that the spring mass system consisting of all these three elements, it is subjected to a force Ft, and the system response is described through the displacement u of t at any time t. Now, one of the basic parameter that is associated with any physical system is how many coordinates are required to locate the displaced position of the mass m. So based on the degrees of a freedom of system that is required to describe the mass position, we have basically two systems. One is a single degree of freedom known as SD of system, and secondly a multiple degree of freedom MD of system. So as the term suggests, in an SD of system, the displaced position of the mass is expressed by a single coordinate. Look into this sketch. You can see that in order to explain or fully describe the dynamic response, only one coordinate is required, that is u of t, that is the displaced position of this mass m from its equilibrium position. But as you can see that it is not possible in all the cases to describe the performance of a physical system through an SD of system. In many cases, we may have to adopt to a multiple degree of freedom system or an MD of system, wherein in order to describe the displaced position of the structure, we may require more than one coordinate. Now, in order to explain in detail or to demonstrate some practical examples of a single degree of freedom system as well as a multi degree of freedom system MDOF, I have provided you two sample cases, and I assume that these two sample cases must be good enough to get a basic concepts of SDOF as well as an MDOF. Look here. In order to explain a practical case of a single degree of freedom system, I have shown a water tank. You must have seen in many of the cases the water tank is supported at some elevation through a system of columns. And here you can see that the geometry is, as well as the material characteristics are prescribed. E is nothing but the Young's modulus of elasticity for the column material, and I is the total moment of inertia of the number of columns about its axis of bending, and L is nothing but the elevation of the water tank. And as you can see that this water tank, it is subjected to an Ft, and we would like to obtain its displaced position u at any time t. So here I have represented the response through an SDF model, wherein you can see that in an SDF model, obviously we need to specify three elements. One is the stiffness. What's the stiffness of the system? So here, as you can see that it's a simple cantilever, right? And we know that when a cantilever is subjected to a load P, the deflection at the free end would be PL cubed by 3I, which means that the stiffness K, which is nothing but the load required to produce a unit deformation, will be 3EI by L cubed. It does mean that if I know the value of EI and L, I can easily obtain the stiffness K of the SDF system. Then obviously we know the mass of the tank along with its contents, that is denoted M at the right elevation. That is very important. And here obviously this SDF is subjected to the same force Ft, and we would like to obtain its response Ut. And obviously we know that the system is solved through an SDF representation, wherein we have got the spring K, the damper C obviously for this example is set equal to 0, and there is a mass M, and it is subjected to an Ft, and we would like to obtain the dynamic response Ut. And here is another example to demonstrate the use of a multiple degree of freedom system, or an MDOF. Here is shown a simple two-story shear beam model. Here, please remember, the beams are so stiff enough we can almost neglect the beam column rotations, which means that in order to describe the response of this building frame, two-story building frame, we require only two coordinates, u1 and u2. And as shown, the building frame is subjected to dynamic forces F1 and F2, which means that this is a very good case for us to represent it through a 2 degree of freedom system. And the 2 degree of freedom system is shown here. And we need to evaluate K1 and K2, which are nothing but the story stiffness at the first and the second levels. And the 2 degree of freedom system is subjected to forces F1T and F2T at the two levels. And the total response of the system is described through the two displacements U1T and U2T. And here is represented the corresponding MDOF system, wherein we have the two masses M1 and M2 subjected to forces F1T and F2T, the total response being described through the two coordinates U1T and U2T. And here, as you can see, that the damping is neglected. So I'm very sure that these two simple examples will demonstrate how any actual physical system can be converted either to an SDOF or an MDOF system. Now, we have two basic terms in the vibration theory, and you need to have a very clear understanding of these two terms. One is the free vibration, and the second one is the forced vibration. Now, what is a free vibration? You can see that there is a term called free. Free means there are no forces acting on the system during the vibration. During the vibration, there are no forces acting on the system. So this is what is being written over here. A structural system, when disturbed from its equilibrium position and released, will oscillate about its mean position of the equilibrium. Look here. Here is shown a simple spring mass system. Now, if you disturb the mass M from its equilibrium position and just leave it, what will happen? This mass will oscillate back and forth about its equilibrium position. Now, this is state of vibration of the structure without any external force. That is very important. In a free vibration, the external force equal to 0. So you may ask, then what is required to start this free vibration process? So the answer is very simple. If we want to introduce dynamics into the system for a free vibration process to start, we need to introduce either an initial displacement or an initial velocity without any additional external load. It means that in a free vibration, the process of vibration gets initialized because of an applied initial displacement or an initial velocity or both, and we don't require the support of any additional external load to mobilize the free vibration. So means in a free vibration, Ft will be 0. That means no external load during vibration, no external load responsible for free vibration. Then what is required for the free vibration? We need to impose some initial displacement u0 or some initial velocity v0 or both, that is u0 as well as v0 both. Now on the contrary, we have a forced vibration. So now you must be able to know what is a forced vibration. If the system vibrates under the influence of an applied dynamic force, then that's a case for the forced vibration. Means that in the case of a forced vibration, Ft will not be equal to 0. That is very important. So remember, for a free vibration, Ft equal to 0, and to start the free vibration, we require either an initial displacement or an initial velocity or both imposed on a system. Whereas in a forced vibration, the process of vibration starts under the influence of an external force Ft. That is, Ft is not equal to 0 for a forced vibration. Now is the damping. So the term damping, I will tell you, is the most vague term in the structural dynamics. And you need to have a concept, a very good physical understanding of the term damping. And remember, to explain you what is damping means is just an abstract definition. Just you consider this mass m. Okay, Ft equal to 0. Let me see that Ft equal to 0. I'm just displacing it, the mass m, for an initial displacement u0 and just leaving it. What will happen? The mass will start oscillating. Obviously, we know that as the time progresses, the amplitude of this vibration starts diminishing, and at certain time t equal to 0, what happens? The vibration almost dies out. That is, u will be 0. Which means that there is some property which is inherent to the physical system which decays this vibration. And this property is known as damping. Or in other words, damping is an inherent property of any physical system by which the vibration amplitude will steadily diminishes with the time. And remember that the damping can take the various forms. In its simplest form, it can be a viscous damping. And when you go to, for example, the higher levels of energy dissipation, for example, you want to study the response of a system under strong excitation of ground motion, or maybe under a blast load, maybe that the damping takes various forms. For example, it can be a hysteretic damping, it can be a radiation damping, so it can be a geometric damping. So there are many versions of damping, and we'll go through this in a later session of our presentation. So now, As we know that damping is an inherent property of the physical system, we can have two types of system. One is undamped and the other one is damped systems. First of all, let me just tell you that theoretically, there is nothing like a term called undamped. Every system will have some damping. But for some mathematical calculations, even if we do not include damping, the results are not getting affected. And in such a case, we can straight away go with an undamped system. So, as the term suggests, an undamped system is realized when we ignore damping. On the other hand, if we incorporate the system damping in our calculations, we end up with the analysis of a damped system. Now, referring to this simple sketch, for an undamped system, we conclude that C must be equal to 0, and when C is greater than 0, we end up into a damped system. Now, is a very important part of the theory of vibration, that is writing correctly the dynamic equation of equilibrium. Now, before introducing you to how to write down the equations of equilibrium for a dynamic system, obviously we know that similar equilibrium equations do exist for static systems. If you want to solve any static systems, either for the external reactions or for the internal forces, obviously we know that the first step involved will be writing correctly the equations of equilibrium. Obviously, for a static system, we know that the equations of equilibrium are simple: sigma F equal to 0. That is, it can take in the form sigma H is equal to 0, sigma V equal to 0. That is, the algebraic sum of all the forces in the horizontal direction or in the vertical direction should be equal to 0. And the other important equation is that the algebraic sum of all the forces, external and internal, acting on the system should be equal to 0 about any point in space. So, similar to this equations of equilibrium for a static system, we will also be able to write down a dynamic equation of equilibrium, whether it is an MDOF or an SDOF system. Here to start with, let me introduce you how to write a dynamic equation of equilibrium for an SDOF system. Here is shown an SDOF system wherein, as usual, we have got three elements: a spring characterized by its stiffness K, a damper represented through damping C, and we have got a mass M. And this spring mass system is subjected to a force Ft, and its response is described through the displacement U at any time t, which is measured from the equilibrium position. Now, just like a static case, we need to consider the free body diagram of the mass M. Now, as you can see that, here I have shown you the free body diagram, wherein the external force Ft is marked. Now, you need to clearly decipher the internal forces developed in all the three elements, namely spring element, damper element, and mass element. Now, let us first focus on what will be the internal force that is developed in the mass element. And here comes the great D'Alembert's principle. What's the D'Alembert's principle? It says that when a mass accelerates, it develops an inertial force. So I have written very clearly inertial force. Remember this, inertial force. And obviously, what's the magnitude of this inertial force? That is nothing but the mass into the acceleration. Mass into the acceleration. So that's the magnitude. And what will be the direction? The direction of this inertial force will be opposite to the direction of motion of the body. Now, based on this D'Alembert's principle, let us mark the inertial force. Obviously, if u is the displacement, we know that the velocity at any time will be du by dt, that is represented through u dot. And the acceleration at any point of time will be d square u by dt square represented through u double dot. It does mean that if ut is the displacement at any point of time, the acceleration of the mass will be m into the acceleration u double dot. So the inertial force will be m into u double dot, and it acts in a direction opposite to the motion. Now look here. In this case, the displacement is to the right of the equilibrium position, right? That is very important. The displacement ut at the time t, it is to the right of the equilibrium position. It means that the inertial force should act to the left of the equilibrium position. So as you can see that mu double dot is correctly marked. So the first internal force is the inertial force. So we have taken care of the mass element m. Now the next one is the damper. Now here we assume the concept of a viscous damping. The concept of a viscous damping is developed such that if C is the damping, at any instant, the damper elements develops a damping force that is proportional to the velocity. And again, this acts opposite to the direction of the displacement. So looking into the sketch, we know that if u is the displacement, u dot is the velocity. If u dot is the velocity, as per the concept of viscous damping, the damping force will be c into the velocity. C into the velocity. So c into u dot. So here I have marked the internal force c into u dot. Now finally, we would like to know what will be the internal force developed in the spring element. And you must be very comfortable with the spring element, because you know that if u is the displacement of the spring element at any time t, the corresponding internal force in the spring element will be k into u. And that is, we call it as the spring force, k into u. This is directly written over here. Ku is the spring force. And remember, it is proportional to the displacement, and again it acts in a direction opposite to the displacement. So we have written down all the internal forces corresponding to the mass element, damper element, and the spring element. And we have got an external force Ft. So now you just write down the equilibrium equation as usual. That is sigma fx equal to 0, which means that m into u double dot plus c into u dot plus ku is equal to Ft. This is what is explicitly written over here. And this is the basic dynamic equation of equilibrium for an SDF system. Remember, this equation has all the terms, that is the displacement u associated with the spring force, velocity u dot associated with the damper, and u double dot, and that is associated with the inertial force. So we have the inertial force plus damping force plus spring force equal to Ft. So I think that's all about this presentation. So I will take you to the various topics in the theory of vibration in the subsequent videos. Thank you for listening.